So using an outside micrometer, device used to precisely measure thickness of blocks, outer and inner diameters, and shafts and depths and slots, just depending on what type you have. We have three types. We have outside, which is what we've got. We've got an inside. Now there could be combinations on the same micrometer, right? You understand that? And then we have depth. Okay? These are all three of them right here. And of course we're using this guy right here. Parts of an outside micrometer. So we have the measuring rods, and what's unique about the one that we have, these guys are capable of measuring all the way down to nothing, all the way up to I think it's up to like 6 inches. So if you look, you have different rods in there that we replace depending on the depth that we're trying to measure. So the smaller the width, the smaller ones would be able to measure up to, I think, 6 or 4 inches. I can't remember. 4 inches. It's on the side of the mic, and then we'll use the long one. So we're going to be probably and then there's one that's already in there, by the way, which will be the one that we're going to use. It's what we do is we change out my camera. Hope it's connected. So what we would do is we'd change out this handle right here, and this would change the length. We got the longest possible one you could have, because we're going to be measuring from 0 up to I think 100 millimeters. I mean, not millimeters, millions. These guys measure in inches. And of course, the American wire gauge that we're using, so we'll use the inch scale, but I think on the lab it's going to ask you also the so we have the locking mechanism on ours. The locking mechanism is not a lever. It's right here up under the thimble. This is where we lock it right here. You know, see what I'm doing? Sorry. Right here. So this is the lock on this one. So if you lock it, then it's not working. Then you should be able to accidentally turn the thimble. Make sense? You okay? And then unlock it to be able to turn the thimble. Then of course we have the actual thimble itself, which on ours would be, and then the ratchet cap. So let's go over. I'm going to bring up the video editor mode. So this right here is the thimble. Okay. And then this down here is what we call the ratchet, and we'll explain the difference. Actually, the bottom of the ratchet cap is what you actually end up using. So we use our thimble to get close, because you can see it moves the bottom handle the fastest. And then when we start getting close, then we'll come down here and use the little ratchet. When it comes in here, we'll move it until it clicks once. And then when it clicks once, that's where you make your measurement. Does that make sense? And then, of course, scale right here. We'll explain the scale. It's not going. The light's not right in here, but this is where we read the scale. So somewhere on here. So if it's adjusted right, when the bottom anvil rises up, it hits the top anvil, and then I'm going to start turning the ratchet cap, and you click it once, and you read it, it should read 0. It's not, then we would adjust the top anvil, or we could actually adjust the bottom. Are we okay? So right here, this is where we're going to actually measure on the scale. And of course, you can get metric scales. So this is a English Standard Scale that will measure down to the thousandths of an inch. There's our scale. Are we okay? Everybody okay? The thimble is rotated to increase or decrease the distance between the anvils. The measurement is read from the numbers printed on the barrel and the bevel thimble, and we'll look at that. So y'all see how y'all do that? You okay? So we start turning. We'll turn the thimble because we can move that bottom anvil real fast. And then when we start getting close, you don't want to hit it with this, because if you do, you might actually put it. If you're dealing with a soft metal, you might actually put a dent in there, right? And then your measurement will be off. So use this thimble to get close, and then start turning the ratchet cap with your fingers until it clicks once, and then you'll read the measurement. So on the scale, what we have is we have a thousandths of an inch. Everybody okay? And then these right here are milli inches. Everybody okay? Does that make sense? Questions on that? So each one of these things indicate a thousandths of an inch, and then the large divisions is milli inches, right? Everybody okay? First, turn the thimble until the space between the anvil and the spindle is wider than the device to be measured. Second, place the device to be measured between the anvil and the spindle. Third, turn the thimble with the ratchet cap until the rods contact the ratchet cap and clicks what? One time. Fourth, tighten the locking wheel. Fifth, remove the device to be measured. Sixth, read the measurement. So that's the procedure for using this. Make sense? Everybody okay? Reading the measurement. First, we need to determine how many major divisions are shown. So right now we see we have how many major divisions that's shown? 5. So that means I'll start off by writing down 5. Are we okay? Then what does it say? There's 5 because the 5 mark is the greatest whole number that the thimble is not covering. On the micrometer, each mark is 1/10 of an inch. Okay. This makes the reading 0.5. Are we okay? Everybody okay? Any questions? Ask now, forever hold your peace, right? Next, we need to check how many minor divisions are shown after the last whole number on the barrel. In this case, so what we're looking at is we're looking at this. So here's 10, here's 10, here's 15, right? Everybody okay? And then we have 1, 2, 3, 4, 5 divisions in between each one of those. Each of these marks is worth 25 thousandths of an inch. So what would I be measuring? But each one of them is worth 0.25, right? So if I put 0.025, and each one of them is worth what? So we got 1, 2, 3 divisions. So what would that be? Yeah, 5.75. 570 or 575 milli-inches. Okay. Huh? Here's 10, right? Oh, it's only 2. So is that right? 1, 2, 3, 4, 5. So the slide's right. Next, we need to check how many minor divisions are shown after the last whole number on the barrel. So the last whole number on the barrel is what? 10. And then we count the number of divisions. 1, 2, 3, 4, 5. So this counts as the 5th, so that would be 1, 2. And that's lined up there, right? You understand? Then we multiply that by 0.25 times 2, so it should be 0.025. Or counting 25s. Can y'all count 25s? Oh, it could be worth 0.25. Figure this out. Okay, so each one of these, next we need to check how many minor divisions are showing on the last number of the barrel. Let me clear out this. So now I'm getting confused. Okay, I'm sorry, here we go. Duh. So let's go duh together. So this is the barrel right here. So, sorry. So that's right. So here's 5. So that's my last number. So I write what? 5. And then I count this. 1, 2, 3. Each one of these is worth 0.25 or 0.025. So that's going to be 7.5. Are we okay? Okay, that's where I messed up. So this is what we got so far. We're not through because now we're going to use this to figure out what the actual reading is. Sorry. So 5, then we count these. 1, 2, 3. These are all worth 0.025. We have 3, so that would give us this number right here so far, right? So we started off where? We started off here. And now what we've done is we've added this. And we're setting at what? 0.575 inches. So let's go to the next one. The first step is to read the thimble. So this is the thimble. Here we're looking for the mark that most closely lines up with the center line. As you can see, what lines up is this guy right here, which is 12. Everybody understand why is that 12? Because this is 10, 11, 12, 13, 14, 15. Okay? Everybody okay? Here we are looking for the mark that most closely lines up with a line. As you can see, the mark lines up with the center line corresponding to the number 12. 2 marks above 10. Each of these count 1/1000th of an inch. So this is what we got. So what we got? We got 5, 0, 0. Then we added 0.25 to that. Now we're going to add what? 0.12. And we end up with what? 537 inches. 537 millimeters. Y'all understand?
You add 25 and 7.
Oh, 75, thank you. I supposed to add 75. I added what each mark was worth. Thank you. I should have raised that other one while I was raising, shouldn't I? 0.587. Okay. 0.587 or 787 million. So this would be a thousandth. This would be 10 thousandths, right? And this would be 100 thousandths, what we call millions. Okay, guys. So what's this guy measure? We got it? So what's my first number going to be? Huh? Huh? That's what I'm asking. What's the first digit going to be? It's going to be 0, right? Okay. And then this right here would be 50 plus 22. 72. Yes, no? Huh? Okay. Abram, you okay? So we look at the last digit we see. What's what we see? 0. So there's a 0. And each one of these are 25. So I count the number of marks I can see. So that'd be 25, 50. And then I add that to it. This is 20, 21, 22, right? Makes sense? 0.072 is what I came up with. Are we okay? .072 inches, or 720, or 72 million inches. Okay, guys, what does this one read? Okay, so we got 0.589 for 1. Everybody got anything different? Huh? What you got, Selection?
I got 5.
Okay, so we come over here, we say 5. So I write down 0.5. And each one of these is 25. So it's going to be 75. I'm going to put it right here. 0.75. And then here's 15. So this must be what? 14. So I'm going to add 14 to that. Add it all together. See what you did wrong, Ira? What do you mean you started from the bottom? I can't hear you. Yeah, but you can't see. 10's over on the side of the barrel. You can't see 10. But I know that's 15. So 1 less than 15's got to be what? 14. You can't start from 10 because you don't see the number. Where's the 10 at? It's on the other side of the barrel, right? Which is because we're looking at this guy here is a circle. We're okay? 0.589. What's this guy? Is Lamar in this guy? Huh? 0 point. What's that? What'd you get over? So the biggest thing we see is 7. So I'd say 7. I can't see this line right here. By the way, if that line was lined up, that 0 would be lined up, right? You understand? So we can't see that. So I'm going to add 0.25 to that because I can't see that line. And it's not on 0. Y'all understand what I'm saying? Yes or no? You can't see a line. So we don't, that's not going to be, we're not going to add 0.05 there because I can't see that other line. Okay. The last line I can see is that line right there. So it'd be 0.25 and then I'd add 22 to that. 0.747. So I think what you did was you added it. Y'all understand if the 0's lined up, that means it's right at it's on the line. Everybody understand? If the 0 is not lined up, that means you don't count a line unless you do what? Unless you can see it. Okay, understand? So just take your micrometer and roll it around to 0. Line 0 up with that guy right there. And you should just be able to see that line right there. And then you would count it. Okay, y'all understand that? But if it's all from 0, if 0 is not there, then if you can't, so you can see that line when you line it up with 0, right? You understand? You should barely be able to see the last line lined up on the micrometer. If you can't, if it's not lined up on 0 and you don't see it, then you don't count it. And you can see we're almost there. We've only got, 2 little clicks away from actually rolling around to the next number. So this is, and of course the numbers go this way, right? And once it gets up to 0.25, 0.025, then it rolls around. So there's only 25 there. Now if it falls in the center or inside this, then that's basically a guesstimation. Yeah, but it's going to be within 1/1000th of an inch, right? You understand that? So that's the micrometer. I mean, we could go in here 0.75. We could do this forever, right? You understand? Once you get the feel of it, and of course, if you dealt with them for years, you wouldn't need a pencil anymore. Probably don't need a calculator. Don't need to be able to do this longhand. Should be too much. So this is not rolled around from 0. So how many points? So I'd come up here and I'd say what? So it'd be what? 6, right? 2, 5, and that would be 3, 5. Are we okay? That makes sense? So some of them you can do. After a while, you'll be able to do it, do them in your head. So this is what we have on the actual micrometer. So we're going to count that one. Why are we going to count it? Because I can see it and it's past 0, right? You understand? So this is going to be what? I'm going to say 2, 1, 2, 3, 7, 5, 7, 6. 276 millinches. And this still is not our micrometer. This one, the lock is right there. It looks like on this one, this came from. Or is that where I don't think that's where the lock is. Yeah, because I locked mine. Or the one I got. So most of the wire gauges we will be able to use with this spindle right here. I called it an anvil, but it's actually a spindle. And then this should take us all the way up to I think this is the 1 inch, right? Isn't it marked on there? So if you run it all the way out from 0, you'd have what? Yeah, so this will take us all the way to 1 inch. So this should be able to measure anything up to 4/0, right? Well, let's see. What's the next one up? 250 mils? So I did give y'all a copy of the American wire gauge, right? And of course, the American wire gauge goes up to 4/0. And of course, 4/0 is a little less than half an inch. So 4/0 is about 460 millinches. And anything above 4/0, they're going to start using what they call circular mills, which is the diameter squared, right? You remember that? No, I don't think any of these. I think this is the one I got to. So this one goes to 4/0. Let's see if we got a table that shows us the standard circular mills. I think it. This goes to 4/0. This goes to 4/0. This goes to. That's too little for us to see. See if they got some images here. Yeah, I can see that one too. But circular mills are, so what would you do to do circular mills? Did we go over that? Huh? I remember we got that far, I think we went through this. No, we didn't. The book. Now, of course, if you want to get the textbook, we didn't order them, but you could probably get it on like Amazon or something like that if you want a copy of it. Some students want that. We're trying to do the PowerPoints. Or was that in the first one? Yeah, we looked at American wire gauge. Okay. Let's look at this one. This doesn't have the wire gauge on there either, so y'all make sure y'all don't drop the mic. So go ahead and put it up, right? Oh, I've got my thimble running all the way out. Everybody okay on conductors, insulators, and semiconductors? We covered that, right? Yes or no? Everybody knows we're going to look at how current flows through the insulator, conductors, and semiconductors. We'll look at the thermal, electrical, and physical characteristics of electrical insulators. And what's the function of the insulator? Right, tries to prevent. There is current flow in the insulator, but it's extremely, extremely low. Everybody understand that? There's current flow across the top of the insulator, which is determined by how dirty the insulator is. And we're going to probably skip over the light, even though it's covered in that first chapter in that textbook. But we have a whole lecture on that, so we'll probably look at it a little bit. We transmit in conductors, especially metal conductors. We use them for two things, right? There are two ways power and information can be transmitted. We can do it through what? Wirelessly through radio, right? And infrared. So a good example of radio, of course, would be your cell phone that you carry around, and of course your radio you listen to in your car, right? You understand. And then infrared most people, when they're at home, they got a remote for their TV. That's infrared. And so this right here is infrared. I don't think this camera will pick it up real good. It might. And of course, infrared is light that we can't see. Right? We can send it through conductors, either metal or optical, and that's what we're doing in this class. We're looking at conductors. So the first half of the term, we're going to look at metal conductors. The second half of the term, we'll play around with optical conductors, what most people call fiber optics. Everybody okay on voltage? All right. Current. Everybody okay there? And then we need to understand resistance and reactance when we start dealing with current. So the other day, when more people were here, we actually saw reactance, right? Did y'all see that? So we started off by rolling this thing out, and it acted like a conductor. And then when we started rolling it in a loop, we got a phase shift, and the voltage drops actually changed inside the circuit. Of course, conductors offer very little opposition to electric current flow, many free electrons, silver, copper, gold, aluminum, and etc. Few hundredths of an ohm per 1,000 feet. Insulators offer an extremely high opposition to electrical current flow. Few free electrons. It doesn't say it prevents all current, it's just extremely high opposition, right? If you've got enough push and you've got a path, the electrons are going to move. Millions of ohms per inch. Semiconductors fall between conductors and insulators. And we use semiconductors for various things, especially in high voltage cable, which we'll look at, our conductors. This looks like the same thing we already went over. So insulators have 5 to 8, right? Okay. Semiconductors are elements that have 4 electrons in the valence shell. Natural semiconductors include this. That's in the periodic table. I think it's 14, column 14. Of course, the most widely used are silicon and germanium. Semiconductors can be used to control the flow of very small applied current. These are bipolar junction transistors. Control current flow with an applied voltage, that's FETs, with a very small applied current. We have diodes which control the direction of current flow. These are the devices that we use to convert AC into DC. Originally, we do a lot more after that. We can make them produce light. We call these light emitting diodes, right? We can make them receive light. These are photodiodes and phototransistors. So when I come up here and hit this, let's see if this, I don't think this camera might pick it up. Turn it away. So this camera will pick it up. And I can't bring up my computer camera. But inside this, we have a photodetector, right? You understand, that receives the light, and then this thing right here transmits light. So that would be phototransistors, which are used most often. Photodiodes are not used that much often anymore, but it still does the same basic function. We can use them to produce electricity. These are photovoltaic cells. Or we can use them to sense pressure, and we can use them to sense temperature, thermistor, and we have many more applications. One of the applications in high voltage cables is to equalize the pressure, and we'll talk about that later on. So we've got some high voltage cable in there, and we'll see there's a semiconductor layer inside there to equalize the pressure around the cable, and we'll look at why for obvious reasons. Electromagnetic waves, these move through a vacuum. Waves that move through a vacuum, of course they move through non-vacuum. AC flow through conductors emits. So AC flowing through conductors emits electromagnetic waves. Everybody understand that? Light is an electromagnetic wave moving at a much higher frequency than AC current. So electromagnetic wave, all electronic magnetic waves move at a rate called frequency, right? We already looked at that. Is everybody okay there? Refraction, the bending of light as it passes through material that conducts light at different speeds, which is strange. So, anybody that's fished or anybody ever did bow fishing, tried to fish with a bow? Yeah, it's very, very weird. If you shoot at the fish, you're going to mess it a long way because of refraction. And what happens is when light moves through objects where it moves at different wavelengths, it bends the light. Literally, the light actually bends. So our eyes are seeing the fish at one place, and actually you'll overshoot it a lot. So it actually goes down and bends down. So we think the fish is closer than it actually is. Attenuation is a very important specification in light. In conductors, we call this the loss of signal over distance. And modulation is when we take information and we change it. We place it on top of a frequency that we call modulation, and that's it. And so if I'm going to send information through the air, and I want to make it unique, so I have the ability to detect it and make it unique. So like a radio station. We got all these radio stations sitting inside this air at the same time. They're all there at the same time. And your cable, you got some cable systems have literally hundreds of channels on that cable at the same time. Well, how can we pick which channel we want to listen to, or station we want to listen to? Well, all the stations are modulators. So what they do is they take that information and place it on a high frequency that we call a carrier. And then what you're doing is when you tune in your radio or tune in your selected station, what you're doing is you're setting up what we call a tuned circuit, which only lets the carrier come through. What does it do to all the other stations? Blocks them, yeah, keeps them out. And then we have circuitry that we strip the carrier off, and once we strip the carrier off, then we've got the information, you got your channel. So, that device if you've got a internet access on your cable, you use a device called a modem, which stands for modulator, demodulator. So a modulator would add the carrier when you put it on the cable, right? And what would the demodulator do? Strip it off, and that's why we call them modem. So that's a modem system. So when you tune your radio in your car, you're setting up a demodulator, but you're selecting the frequency that your demodulator works at. So your phone's got a modulator, demodulator in it, right? You understand that? So when you talk, what does it do? Well, before it goes out that antenna, it's going to be modulated and placed on a carrier. Then the antenna receives the carrier, it transmits the carrier, and then when somebody calls you, then your phone sets up a demodulator so you can, from that number, so you can detect it, right? Which is pretty neat. So we use modulation not only to modulate light, we also use modulation to modulate electricity. And so your cable is actually modulating electricity, right? Light sources, optical fibers, are modulating light. And I wish I could show you this. I need to give me an application so I can look at my camera. On my laptop. My laptop adjusts for light, so you can actually see the thing flashing. Fiber optic cables can carry very little energy. So when we use conductors, This should be in this PowerPoint. We use conductors for two different things, and I think what are the two things that we use conductors for? Anybody guess? Yeah, one thing we use them for is to transmit power. And then the second thing we use them for is what we call signals or information. So when we send, or we can use them both at the same time. Of course, signals are not designed to provide power, so we don't power up off of signal cables. So your TV does not power up off your cable. Now, if you've got what we call a landline, if you got a phone, a real phone in your house, it literally powers up off the signal wires. So the signal wires and the power wires are exactly the same thing. So it sits there about, when you pick it off the hook, that puts powers your phone up, and then it's about 20 something volts, and when a ring comes in, it goes up to about 48 volts. So don't strip those wires with your teeth, right? Now, optical cable, we can't send power over optic, so all we do on fiber optics is we send information or data. Make sense? And that's what this says, by the way. So fiber optics carry very little energy, only used to transfer information. Because of higher frequency, it transmits enormous amounts of information. And what's very important is this last thing. This is not affected by capacitance, inductance, electromagnetic interference. So when they ran the network from a building over here, they did not use copper. They used fiber. Even though we didn't get an increase in bandwidth, it was safe to run outside because it's not susceptible to lightning strikes. We blew up all the network cards. When we first started doing our cabling, we literally blew up all the network cards in a whole lab because the cables didn't run outside. So lightning struck, that big EMF pulse came in, hit all those network cards, and literally blew the network cards up in all the computers. Luckily, that was in the day where the network card was put in as an option. So we plugged it into what we call an expansion slot. So we were able to replace the network cards without replacing the computers. This guy right here, though, it's got a network cable interface on it, and it's part of the computer. So if I blew up the network card on this, I couldn't replace it, right? So running over to the MillSAP, we run fiber. Running over here, we run fiber. That way, if lightning strikes, they were going to run some cable over there, and they asked me my opinion. They were going to run it across the top of the building over an A building because they had to go through a firewall. And there's a lot of specifications when you punch through a firewall, how the holes have got to be sealed up and everything. So what they decided to do was just run the cable across the ceiling of a building. Yeah. Not affected by capacitance, inductance, or electromagnetic interference. So this is a big advantage of fiber. We don't have to worry about, we can run it through very electrically noisy environments without worry about interference getting into it. Electrical conductors can carry what? Yeah, so here we're talking about metals. We can carry power, we can carry information, we can carry both. It's less expensive than fiber optic systems, but here we're subjected to capacitance and inductance. So if I run two cables side by side, they can couple with each other, right? If we put AC in. If I put twists and turns in cables, then we have an inductor, which is going to greatly affect the operation of the cable. We don't have to worry about that in fiber. We do have to worry about the bend ratio in fiber because of what we call refraction, and we'll look at that. So when you loop your fiber, you're supposed to put it in a certain radius, because if you don't, the light will go out the side of the cable, and we'll look at that when we get it. Attenuation, what's attenuation? So we're not going to talk about cladding, we're not going to talk about critical angle, because those deal with fiber, and we're going to have a whole lecture, a whole section on fiber. So we're going to be looking at attenuation. We're going to, of course, a conductor. What's a conductor? What's that? Well, fibers conductors too. So fibers are just used to carry, information. Or, but in electrical conductors, these are wires. We'll look at the dielectric strength, of course, the equivalent circuits. So we got to see, well, insulator, of course, we need to look at semiconductor, tracking, treeing, and volumetric current. Get some of everybody okay with Ohm's law? Okay. Of course, that's our relationship between the voltage current. So normally what we would like is we'd like an electrical conductor to look like this, or any conductor to look like this. But in actuality, this is what the conductor really looks like. Now, what determines the resistance of an electrical conductor? Yeah, so the material it's made of, right? And then, of course, the what? Length. And then 3, the size. And then 4, the temperature. And of course, in metals, when temperature goes up, opposition goes up, right? Everybody okay? Any questions there? And if you're an electrician, that's what you're very concerned with, to even gauge the wires. There's really good tables inside the National Electrical Code book that helps you gauge wires, depending on what. Those 4 characteristics right there. Insulators. So this is the equivalent circuit of an insulator right here. DC and AC. DC, we wouldn't be concerned with that guy right there. And because the amount of reactance we get, how much that affects our circuit is equal to this. Now, whether we in AC, you will learn this formula and you will deal with it a lot. But what this F stands for is frequency. So what that means, and how much frequency does DC have? Should have pretty close to what? 0. And anytime I divide by 0, we come up and get infinity. So basically, a conductor, we're not concerned with X of C if we're using DC. And we're not concerned with X of L if we're using DC. So this guy called X of L, which is inductive reactance, is 2 pi FL. Now C and L, these are the size of the device. So when you go out and buy a capacitor, we buy it in what we call farads. That's the physical, not the physical size. That's the storage size, or that's the size. That's the I guess you'd call it the electrical size. That's what your electricity or your frequency says. It don't see a physical size. It sees a storage capacity size. Everybody understand that? And this is in farads. And then this is in what we call henries. So this guy here has so many henries, not according to its physical size, but according to the loops, the spacing between the wire, and then what material we wrap this around. depends on what we call the Henry's. And so the size of the conductor, not the physical size, would determine how this thing responds to frequency. So if we're using DC, then we're not concerned with what? We're not concerned with X of L, and we're not concerned with X of C if I'm trying to send to there. But we're very concerned, so what we'll be concerned with there is R. Make sense? Because that would determine the amount of voltage drop. So what we end up here is we end up with an equivalent circuit where this would be for this looks like this is for a coax cable. Everybody ever seen coax? You don't understand coaxial cable? I'll go ahead and take a break. Let me go get some of these cables. This is a coaxial cable. This is what's running into your house from your cable. That's why they call it cable TV. And it consists of, and it's kind of misnumbered, and we'll talk about it later on, or misnamed. But our two conductors, there's two conductors in here. And I know this is not focusing in real well, but it's got on the out, it's got in the center, it's got a conductor. And then it's got an insulator. I can't see if I can get it in closer. I don't know why my camera's not focusing. Then we got an insulator, conductor, and then we have what they incorrectly call a shield. But that's just the name it gets, which is a conductor that's wrapped around the outside of this insulator. So measuring the gauge of this guy will be easy, but the only way we can measure the gauge of the shield is to pull it out long enough and twist it together as tight as we could to measure the size of the gauge. This is called coax cable. And we don't transmit DC to this thing. Usually we transmit AC at a pretty high frequency. So what I end up with is I end up with a plate, an insulator, and a conductor. So these guys right here basically act like a capacitor. Everyone comes to this. And this is what we call coaxial cable, or coax cable. Which would basically be what they're illustrating here. So what we have is we have a center conductor, and then we have a insulator. So here's our insulator. And then on the outside of the semiconductor, we have a shield. What they call a shield, but it's actually a conductor. But it will be your return conductor, which is usually connected to common or ground. So this is the equivalent circuit for that conductor. So that's the equivalent circuit for the coax cable. Where the R would be the R of the wire, and then that shield, the shield would be the conductor. So this is not exactly right, but it's good enough to get a feel of what's going on. So what's going to happen now is if we got that thing right there, then this formula right here is going to come into play, and there's a little more to it, but this is good enough. But that C only comes into play if you're running what really? AC. If you're running DC, it acts like an open. The capacitor does not come into effect. Everybody understand that? And so these are communication cables, and communication cables are special. So later on, we'll look at something called impedance matching, which is very, very important in communication cables. Not very important in power cables, but in communication cables. So you got to be real careful with this wire when this conductor when you splice it, or even when you terminate it, because you can't change that C. Everybody understand that? If you change the C, then you change the opposition of the cable that it offers to AC. I tell you about my father-in-law breaking his cable coming from his, and he couldn't understand why he got, because he went out there and did what? Stripped it, twisted the two together, wrapped it up with black tape, and couldn't understand why his picture got so bad. Because he screwed up that C. He changed the spacing between those cables and messed up the capacitor that's got to be in there for those cables. Current flow in the insulator. So the formula is I is equal to E over R. IC is equal to E over X of C at 90 degrees, which what happens on a capacitor, it's like a bucket. If you can understand water buckets, you pretty much well understand the way a capacitor works with electrical current. So when the water bucket is empty, how fast can you put the water into the bucket? Real fast, right? Now what happens is that when the bucket starts filling up, then the flow rate of the current goes down. And of course, once you fill it up, it don't overflow, it just stops. So that's the way a capacitor works. Well, what happens is when we're down here empty and we start filling it up, we're filling it up fast. So the opposition in ohms when the capacitor doesn't have any water in it is equal to about 0. So if the opposition is 0, then the voltage drop is, if V is equal to I times ohms, then the voltage drop across the capacitor starts out with 0. So as soon as you start pouring that in, current flows maximum, but voltage across it is 0. Y'all understand? But that's opposite from a resistor, because a resistor says if I put current flow through it, I get a voltage drop. A capacitor, when you start pouring the current in there, it actually has no voltage drop. And as the voltage goes up, then what happens is the flow rate in the capacitor goes down until it drops all the voltage. So when the capacitor is dropping all the voltage, there's no current flow through it, into it, which is opposite of what we learn about resistors, right? So resistors, when you measure the maximum voltage drop across the resistor, the current flow through it is maximum. And a capacitor, when you measure the maximum voltage drop across the capacitor, the current flow in and out of it is actually 0. So that means what we do in a capacitor is we get what we call a 90-degree phase shift in the current, between the current and the voltage. I guess they're weeding. And this is what creates these phase shifts, is that 90-degree phase shift. Now, what you don't see is you don't see 90 degrees. If I come up and did this, and I looked at the phase shift of the circuit, it's going to be what we call the vectored sum of the two. Does that make sense? So the analogy we use is these flying cameras that they have over football games, where we come over here and we have reels set up on the corners, and then we have cables running like this, right? You understand? And then the camera is mounted right there. So what determines the angle is how fast these motors are moving. Now the angle that the camera moves is determined with the speed. So if they're running at the same speed, then it would move at what? It would move at 45 degrees. If one set is running and the other one is not, then it's going to move at 90 degrees. Well, what we're seeing is we're seeing the current flow in the circuit is being varied by the resistor, where we have no phase shift, in the capacitor where you have a 90 degrees phase shift, and we end up with a vector. Does that make sense? So over here, this motor right here is running at 90 degrees. This guy here is running at 0 degrees. So what happens is you end up with a phase shift in the circuit depending on the voltage drops or the speed that we run. A capacitor is created when two conductors are separated by an insulator. Everybody understand that? So that means I've got an extension cord and I've got two wires running in there. You create a capacitor. But why don't it affect us in Alabama Power? So here we're going to have a capacitor. If you got a little twinplex cord, you have a capacitor right there. It's going to be way down in probably the nanofarads, which is 10 to the -9. Your frequency is only 60 hertz. So that's not going to affect you at all, right? Because the frequency is so low. But if we were to go out there and put a cable TV channel that's moving at 100 megahertz, then now that little capacitor is going to start causing problems, right? You understand that? Virtually all the electric circuits exhibit capacitance. Capacitance current IC leads the resistive current by 90 degrees. X of C is determined by the what? The material, the length, the thickness, and of course the surface contamination. Approximately 100 times greater current is than IR in the insulator. And that's just an approximation. But there is current flow through the insulator. Y'all understand why? Why? Very little, but why? Because there's a path. You have push, and there's a path. So that's just like me. I come up here and pick up a AA battery, and I put my two fingers like that. There is current flow through my body. Right? You understand? But I probably got 200 or 300 kilo ohms worth of resistance, but I still have an I is equal to V over R, right? You understand? And of course, the current would be right that way back down there in the picoamps, but there's current flow through your body. So there's current flow through your body all the time. If I come up here and touch a piece of metal right here and touch a piece of metal over here, even though they're grounded, there's current flow through ground. Because it's impossible for me to put everything, if I don't ground everything at the same point, well, the wire length that I have between the ground post on the side of my house and the length of wire that ground runs, there's an R in the wire, right? You understand that? And if I have a difference of potential, I have current flow. But all your current flow, 99.9999999% of the current flow is through the conductor. The other very, very small part is through the what? Insulator. And the insulator is going to cause a phase shift because we have two devices, and it's going to cause a capacitive effect. But 60 cycle, it does not hurt us. The R in the insulator is determined by the material and its thickness. So what's the volumetric current? Yeah, so this is current flow through the insulator. Surface current. What's surface current? Yeah, what determines the amount of surface current you get? Yeah, how contaminated the surface is. And we literally got places where the conductor gets the insulator really gets contaminated, and there's quite a bit. That could be quite a bit of current, especially if the contaminant is a conductor itself. Yeah, it's bad, and they don't clean those things off, and your conductors start getting hot. Huh? And it will, because then it'll and then if you ever get an arc through an insulator, then you get what we call tracing in the insulator, which is not good. So surface leakage, y'all okay on those terms? Surface leakage current and volumetric current. We okay there? And this is what we happen. So since the IC and the IR by 90 degrees, the total current in the insulator is the vector sum of the two. And this is not something that we need to learn. In AC, you're going to learn it. In this class, all we need to do is understand that there's what? There is current flow in the insulator. And it's out of phase with the current flow in the conductor. Current flow in the insulator is predominantly capacitive, which means it's what? Affected by, starts with F, frequency, yeah. So it's more prevalent, causes more problems at extremely high frequencies than it does at Alabama Power. Transformers get more efficient the higher the frequency. If you looked inside a switch and power supply and looked at the transformers, they're little tiny things. But the problem with the higher the frequency, the more problems we have with sending it because of what? Because of this, and then also inductors. So 60 cycles is and how they came up and decided to use 60 cycles, I haven't got the slightest idea. But over in Europe, they predominantly use 50 cycles. Over here, we use 60 cycles. Some countries, if you ever looked at the frequency, the power frequency charts, some countries use different frequencies depending on where you live at. I don't know how they came up with that, but I mean, some of them use 50, but the predominant transmitted frequency is 50, 60. But the higher the frequency, the more efficient your transformers become. You can make them a lot smaller to transfer the energy. But the problem is that now you got to deal with all this surface capacitance and all these turns in your cables and stuff like that. So we've been using 60 cycles. I guess I probably need to research that, but I think we've been using it ever since they decided to generate the power. Changes in ratio indicates a problem with the what? Insulator. And they do have inductor checkers where they can actually check this. And this is all we're going to talk about. What we really need to do is talk about gauge, more important. Everybody okay so far? So did I pass the coax cable around? Because that goes in one of the bags y'all are going to be using. I'm sorry. Well, that's what we call coaxial cable. And what you need to look at, it's set up a capacitor. And the spacing in there is very, very critical. So if I was to run over this with a forklift or something and squash that insulator, then now everything's going to be wrong. And like I said, later on, we'll look at something called